You are handed an array of numbers. For every position in the array, combine the values of all other numbers, isolating and excluding one specific piece at a time. The intuitive math solution is straightforward. You calculate the total product of the entire array first, and then, as you move through each position, you simply divide that massive total by the current element's value. But here is the strict constraint that makes this a classic interview problem. The division operator is absolutely forbidden. To solve this, you are going to code the optimal solution from scratch. We will cover a memory trick to anchor the logic, and we will build a structure that naturally steps around the trap of zero-value edge cases. Relying on division is a math workaround. Taking it away forces developers to prove they understand how data flows sequentially, tracking how a single index relates to the rest of the array. The mental framework needed to bypass division requires separating the array into two distinct, manageable halves. We use a simple mnemonic for this: left, right, multiply, or LRM. Here is our base array containing the numbers 1, 2, 3, and 4. Let's isolate and target the third position, the number 3, to see how this framework operates. The left step asks us to identify and group every element that precedes our target index. We take the 1 and the 2 and multiply them to get a left product of 2. The right step requires us to identify everything following the target index. In this case, we just have the standalone 4. For the final step, multiply, we combine the isolated left product with the right product to determine the final value for our target index. 2 times 4 gives us 8. This strategy shifts the focus from a single division to calculating how a moving prefix and a moving suffix intersect. To see if this holds true for every index, we need to apply this logic across the entire array. To apply this logic systematically, look at this trace table mapping our array against our prefix product, suffix product, and final output columns. We execute the left pass first, sweeping from left to right. For each position, we calculate the running product of all numbers immediately before the current index. The first index has no preceding numbers, so it defaults to 1. As we trace the rest, the resulting prefix array fills in as 1, 1, 2, and 6. The first half of the logic is complete. Now we execute the right pass. Moving backward from right to left, we calculate the running product immediately after each current index. As we calculate each suffix value, we multiply it directly against the existing prefix value stored in the output array. This reveals the final correct array: 24, 12, 8, and 6. This two-pass sweeping method mathematically guarantees the exact products for every position. We get the desired output while completely bypassing the division constraint. Let's translate this visual logic into a standard Python code structure. Look at the code building on the left, next to our trace table. We initialize the output array with 1s. Then we construct our first for loop to govern the left pass, writing the running prefix multiplier into the output array at each step. Next, we construct the reverse loop governing the right pass. We iterate backwards, multiplying the running suffix into the values we just stored. Watch the index boundaries here. An off by 1 error at this step will offset your products, causing the entire result to fail verification. You must store the running multiplier in the output array first, and only update the multiplier afterward. Let's test your understanding of this logic. Look at these 3 edge cases: negative numbers, a single 0, and multiple zeros. Pause the video and mentally trace the logic. When the logic interacts with a single 0, the 0 correctly zeroes out the final product for every other position, while its own position cleanly outputs the product of the remaining numbers. If the array contains multiple zeros, they act as absolute nullifiers. Every single position in the final output array will correctly resolve to 0. This multiplication-based approach processes zeros as standard values, preventing the runtime exceptions that occur when a division-based solution encounters a 0 in the array. Let's evaluate the performance metric for the algorithm you just built. Look at this diagram detailing our big O notation. We have achieved an O of n time complexity. The time complexity scales linearly because the algorithm only requires 2 straightforward passes through the data, regardless of how large the array gets. Even better, we achieved an optimal O of 1 space complexity. The only extra memory required are these 2 solitary tracking variables. In algorithmic interviews, the final output array does not count against your memory footprint. By writing our prefix and suffix data directly into that final array, we negate the need to build separate tracking lists, achieving that O of 1 space. You understand the logic, and you understand the constraints. Now close this video, open a blank file, and leverage the left-right multiply mnemonic to rebuild this highly optimized code entirely from memory.